Here we're looking at tables. The first thing we want to check if we're trying to determine what function type we have is that we can look for a common difference. So if we take the difference of two consecutive values, you'll see that the difference between any of these pairs of consecutive values is 2. So the common difference is 2, which means this is a linear function type. A linear function, if you graph it, would have been something in the form of a line. And one way that you can write these functions is using the mx plus b form, where m is the rate of change, or the 2, the common difference in this example, and then b would be the starting value, or the y-intercept, which would have been 3 because we have an x value there of 0. For the second example, we've already checked. Let's assume we've checked and there's no common difference. So another thing you can check for is a common ratio, which we can find by taking two consecutive values and dividing one by the value that came before it. Check with these also. 12 divided by 48 is also 1/4. Do it one more time. 3 divided by 12 is 1/4. So the common ratio is 1/4. This tells us that it's an exponential. Those are characterized by having kind of a steep side and a slow side. So maybe there's a steep side here, and then it gets slower, and it kind of plateaus or flattens out. The form that we can use is a times b to the power of x. The key characteristic is that the exponent is where you're going to see the variable. If you've checked for a common difference, here I'm just subtracting values. I'm noticing that I'm not getting the same number. But if we check for a second common difference, which means the difference between these, so I would take 7 and subtract 3, and I would take 11 and subtract 7, you'll see that they both have a second common difference of 4. So there is no common difference, but there's a second common difference of 4. This is called a quadratic. The shape is a parabola, and we would have ax squared plus bx plus c for their form. So characteristics would be x to the power of 2. In this example, we are trying to decide if it's a linear, quadratic, or exponential pattern. And they said that we're talking about the new tiles that are added. So if we go from design 1 to design 2, these 8 tiles were added. And if we go to design 3, you can see that there are 16 tiles added. And we had already talked about this example in class, but if we looked at the next one, it was 24. So if we take those 8, 16, and 24, and we check for a common difference, if we subtract 16 by 8, we get 8, and if we take 24 and subtract 16, we also get 8. So they have a common difference of 8, which means it is a linear pattern. So now we have a student who has written an expression to represent the tiles that need to be added to get design 3, and we're going to turn that into an expression with a variable. So this student looked at it as there's these 4 sides that have a length of n. The design number, in this case it's 3, so there's 4 sides with a length of n, and then you have these 4 corners. So we'll add on those 4 corners. These two students have also written expressions for the same tiles. they said that there's these two longer rectangle sides, and since this in here is the design number, it's the design number plus 2, because we'll have the left and the right tiles, and since there's 2 of those, we're going to multiply that whole thing by 2 to take care of the 2 rectangles. And then we also have these 2 shorter rectangles. Again, I'm using 2 because there's 2 of them, and their length in, or the design number. Tyler down at the bottom is doing something similar. He's saying that there's these 3 side lengths and there's 4 of them, so he's going to add 3 plus 3 plus 3 plus 3. So if it was a design 5, it'd be 5 plus 5 plus 5. So we're going to go with n plus n plus n plus n. Again, those are the 4 side lengths of design in, plus these 4 corners. So we'll always have 4 corners, so it's going to stay a 4. Now if we compare these two to the one that Wilma had 4n plus 4. If we use the distributive property to multiply, 2 times n is 2n, and 2 times 2 is 4. We'll bring down that plus 2n, and we have some like terms because we have n to the power of 1. 2n plus 2n is 4n, and then that plus 4. You can see it is equivalent to Wilma's. Same thing with Tyler's. If we combine the like terms here, there are 1, 2, 3, 4 n, and then your plus 4. So all of them are equivalent. With this last student example, they looked at it as a big square, and they said that this is the side length of n, so the full side is going to be 2 more than that, because you have 1 at the top and 1 at the bottom. So to get the area of all of that and getting all of these tiles in between, you'd have n plus 2 along one side and n plus 2 along the other. So multiplying those, we get the area of all of those tiles. And then if we take these in the middle and subtract them, we'll be left with those green ones on the outside. So that red square that I have would be n by n. And also showing that it's equivalent to Wilma's, we'll use our distributive property. We're going to take n times n, which is n squared, n times 2, which is 2n. We're going to move over here and do 2 times n, and then 2 times 2, and we're going to subtract this n squared. Well, look what happens. Those n squareds cancel because we have n squared minus n squared. We're going to combine the 2 n's to make 4n by adding like terms and bring down the plus 4. So it is equivalent to Wilma's.